telescope. And by small, it was about as big as this stage, really. My director had a really nice idea. He thought, as the sun sets, we'll sit you on this island and we'll set the camera up. And can you just think, just talk through some of the things you've learned? And I had quite a blank mind. I didn't know, but I just thought, it's a beautiful setting with the ocean backing up on the beach. And I noticed just a few blades of grass. There was virtually nothing on this rocky outcrop apart from some grass, little bits of grass. And I thought, I know about this grass because I've learned about biology for a couple of years now. And for example, you start asking questions. The great physicist Richard Feynman once said that everything is so much more beautiful. Nature is so much more beautiful when you know the detail. Right? There's a very famous story about actually with an artist talking about a flower, and the artist said, "You physicists, you deconstruct the flower, and you remove the beauty." And he said, "No, it's not really when you know the processes that go on inside the flower. You ask questions about the colours of the flower. Why they're coloured? Because it attracts insects. How does it do that? Is there an aesthetic sense of insects when they do the beauty of the flower? It enhances it. Knowing about something, and I can't see how it subtracts. Knowing, and this blade of grass, I saw it and I thought, why is it green? Well, we know why it's green. It's got chlorophyll in it. There's photosynthesis. Why are most plants green? Why is that common? It's common because of these structures called chloroplasts. The chloroplasts do the photosynthesis, but they're almost certainly bacterial in origin. Every photosynthesizing plant on Earth shares these structures. The reason that they all share the structures is because they come from a common source, and the source is probably cyanobacteria. So it's thought that cyanobacteria were the first things to build the intricate machinery of photosynthesis. In a primordial ocean, back 2 billion years ago or more, they put this machinery together that allows them to get water molecules and allows them to allow sunlight to split the water molecules. And then they want the electrons, actually, and the oxygen comes off as a byproduct, which about 550 million years ago oxygenated the atmosphere very rapidly and paved the way for complex organisms like us. So you realise that the whole history, the history of planet Earth is written into this one blade of grass. 3.8 billion years, an unbroken chain back all the way through every organism back to the common ancestor which existed on Earth 3.8 billion years ago. It's absolutely beautiful. And as Feynman said, knowing that only surely adds to the wonder. Because we finished it.
I think you won the biology today, but do you want to do some physics now?
Yeah.
Let's talk physics. It is Brian's specialty. You said in an interview last year that this is an amazing time to be a physicist.
Yeah.
And when you think about it, like in the last century alone, we saw Kitty Hawk going from getting a plane 3 metres off the ground to landing a device on the moon. We went with the initial computers that were 3-storey buildings to having phones in our hand that tapped into the internet.
Yeah.
We went from a man called Peter Higgs, who had a bizarre idea that could answer one of the deepest questions of all time. And within his lifetime, we built the great device that proves it to be true. Brian's going to take us inside the Large Hadron Collider. Brian Cox, ladies and gentlemen.
Back to physics, away from the arts. As Adam said, as I mentioned, I think the Higgs discovery, which is a great discovery surely of this year, but also I think undoubtedly in my scientific lifetime, and arguably, or perhaps not arguably, one of the great discoveries of the 21st century, indeed the history of science. And I'd like to explain why, because that sounds perhaps quite hyperbolic. It's often seen as the fact that we built a big machine and discovered another new particle. But it's significantly more than that, because the story of the discovery tells us that we understand how nature works in a very precise way. And it comes down, as I mentioned, to the unreasonable effectiveness of mathematics and the physical sciences. So we look back to this picture, the 10,000 galaxies in the Hubble Extreme Deep Field, 340 billion galaxies in the observable universe. What we discovered through the 20th century, essentially, 20th century particle physics is that they are built, everything is built of just this set of subatomic particles. And in fact, you and me and the Earth and the Sun and every star and every galaxy we see in the sky are in fact built of only 4 of them. You need 4 to make up us, just assembled in different ways. You need electrons, which is this subatomic particle here. The first fundamental particle, as far as we know, they're still fundamental, to be discovered in 1897. And then these two, the up and down quarks. Now they're perhaps unfamiliar, but they form atomic nuclei. So 2 ups and a down make a proton, and 2 downs and an up make a neutron, and our nuclei are made of protons and neutrons together. So essentially you are a combination, a complex combination of just 3 particles, up quarks and down quarks, with electrons going around them to form atoms, which then bond together into molecules and DNA and the structures of your body. That's true for the Earth, that's true for the Sun, everything we can see in the sky. Then there's this particle here, the electron neutrino, which forms that group 4. Perhaps unfamiliar. The best way to explain, I think, what they do is to look at this spectacular image. It's not a graphic, it's a video image of the Sun, our nearby star. You can fit 1 million Earths inside this ball of plasma. It's a remarkable thing. It shines by burning 600 million tons of hydrogen into helium every second. 600 million tons a second. And if you think what that means at a fundamental subatomic level, what's happening is hydrogen, which the nuclei of hydrogen are single protons, are being merged together. You get 4 hydrogens, you stick them together, 2 of the protons turn into neutrons, and you make a helium nucleus. So the first stage of fusion in the Sun is that protons have to turn into neutrons. They do that through the action of something called the weak nuclear force, and when that acts, neutrinos are produced. So think how many of those neutrinos are produced every second. Think how many protons make 600 million tons of hydrogen. Billions of neutrinos streaming out of the Sun. There are in fact 60 billion per centimetre squared per second passing through your head now from the Sun. The nuclear reactions in the core of the Sun. You don't feel them, and in fact most of them pass through the Earth unimpeded because they interact with matter very weakly, but they're absolutely fundamental to that process, the beginnings of fusion in the Sun. So they're important, if not obvious or visible. And that seems to be everything you need to make a universe. The 4 particles in that group, that family of particles. For some reason, nature saw fit to make 2 copies of those 4 particles, which are identical in every way except they're heavier. And nobody knows why nature chose to do that. We have very good evidence there aren't any more, certainly in this type of particle. There's a 4th so-called generation. But why nature chose to do that, we couldn't tell. Discovered experimentally, one of the great surprises in particle physics when these other particles kept turning up. So for example, this one here is called a muon. A muon is identical to an electron in every way except it's heavier. This one's called the tau, identical to the muon and the electron except they're heavier. Same for the quarks. This is called the strange quark, same for the down quark. This is the charm quark, same for the up quark. And these 2 are the top and the bottom. And last time I said that, last night in Sydney, everybody laughed. Bottom. The people started chuckling. It was like a very juvenile audience last night. And I had to say that in a very biblical truth and beauty, and everyone relaxed again. But it really was. There was about 100 people when he said bottom. But it's called the bottom one. So anyway, there they are. 12 particles in 3 families. There will be a reason, by the way. There must be a reason why that pattern exists. Now, if you think back to the periodic table, if you remember your chemistry from school, back in the 1860s, Mendeleev wrote down that periodic table, arranged the elements according to their properties, and that was one of the keys to the idea that atoms have structure, one of the doors that opened to allow us to understand atomic structure. So there must be some underlying reason for that pattern, but genuinely don't know what it is. And then there are these particles here, the force-carrying particles. Now, that might seem like an odd concept, but quantum theory tells us that forces are carried by particles. So a particle physicist would, if you picture 2 electrons coming together, they have negative charges, so they repel each other. And the picture is, as they come together, photons dance between them. There's called exchange particles. They carry the electromagnetic force. And so the photons bounce and bounce, bounce, they carry the force, and the electrons deflect away from each other. The force carriers of electromagnetism are called photons, which also are particles of light. So the stream, the rain of photons cascading down to the stage now, we consider as a rain of electromagnetic charge carriers, if you like, falling down on the stage, the photons. Likewise, the quarks stuck together inside protons and neutrons by the unimaginatively named gluons. And then there are the W and Z particles which carry that weak nuclear force that I mentioned in the sun, which producing those neutrinos and allowing hydrogen to fuse into helium. That's it. That's 3 of the 4 forces of nature. The only other one is gravity. It doesn't feature in particle physics because it's extremely weak. It's the weakest force we know of in the universe. It's a million times weaker than all the other forces, the other 3 forces. We don't know why that is. You can see it's weak because I can pick something up off the ground. I can pick this clicker up off the ground, and the whole Earth is trying to stop me doing that. As a planet trying to pull that down, it can't do because gravity is weak compared to electromagnetism, which is the force in my muscles. It's allowing me to pick it up. One of the great mysteries. But apart from gravity, then this is the full picture. All the particles of matter, all the forces that stick them together and allow things to happen in the universe. Now, one of the great triumphs of the 20th century was that a single equation, a simple equation, was derived and written down, which describes everything that I've just spoken about. There we go, I don't say anymore. It's all in there. This is called the standard model of particle physics, and although it's kind of, it looks complex, and indeed it is complex in some ways, it's very economical. You can write this on a t-shirt, and it describes everything we know of in the universe, other than gravity, at the most fundamental level. So the most detailed way we know that nuclear interactions take place. Electricity and magnetism. Maxwell's equations, which describe electricity and magnetism that were derived in the 1860s, in here. All of nuclear physics is in here. It's a triumph. But the fascinating thing are the bottom 2 lines here. So the top 2 lines just describe, actually these are the particles in those 2 terms there, and these are the forces allowing the particles to interact with each other. The bottom 2 lines though describe something completely different. They were inserted, or initially conceived in the 1960s by physicists, amongst whom was Peter Higgs. And they do something very strange. We spoke about the aesthetic, briefly touched about the aesthetic nature of mathematics and the aesthetic nature of some mathematical predictions. In the 1920s and 30s and 40s, when a quantum theory of the forces was being developed, it was noticed that there's an important role played by something called symmetries. A mathematician would call them symmetries. So a simple symmetry is to imagine a ball, and a spherically symmetric ball will be described in that way because you can rotate it around at any angle and it looks the same. So that's a property of the ball, an interesting property. It could almost be said to characterize what you mean by a ball. It's the same in every direction. In the same way, mathematical equations can be like that. The symmetries are more abstract, but it's still the same idea that you can characterize the beauty, the structure of equations by looking for the symmetries that they obey. Now it was noticed that the forces of nature themselves really pinned down in a mathematical sense by thinking about the symmetries of equations. Now, I don't ask that you understand precisely what that means, but the idea is that you've got there's an aesthetic reason why the forces of nature exist in a sense. If you're a mathematician, a pure mathematician, you would say that they exist because of certain symmetries. In fact, you often hear these force carriers referred to as gauge particles or gauge bosons. That refers to something called the gauge symmetry, which is a symmetry of the equations, the underlying equations of nature. So they're very powerful symmetries, and mathematicians and theoretical physicists get very attached to them. But what's noticed is that while the forces of nature could be explained in this very aesthetically pleasing way, it didn't work. It broke down if you introduced mass into the equations for the fundamental subatomic particles. Now, self-evidently, particles have mass. We are made of massive particles. So it would seem to be an insurmountable obstacle, although it was interesting and strange that these symmetries almost seemed to work. This aesthetic beauty almost seemed to be realised, but it was ruined by the ugly fact, as Einstein sometimes said, of the fact that we know that particles have mass. In the 1960s, Peter Higgs and others found a way around that, a mathematical way around that. But it was a bit odd, it has to be said. One of the odd ideas that came out of the 60s. I don't know what he was doing. But essentially the idea was this. So as the universe expanded and cooled, we've talked about this before, structure crystallises out. Less than a billionth of a second after the Big Bang, said Peter Higgs, something condensed out into empty space. It's often referred to as a condensate. And it's analogous to, if you imagine water vapour in the air on a winter's day, then that water vapour can touch a window, and the window can be colder than the air. So ice crystals form on the window. So the water changes states. It's called a phase change. It changes from vapour to solid, and in that process, structure forms, the ice crystals. In the same way, quite closely, analogous actually, the universe expands, it cools, and it becomes favourable, energetically favourable for something to condense out into empty space. That thing is the Higgs field, Higgs particles, if you like. So you're to picture empty space, the vacuum, to be rammed full of Higgs particles, a condensate of Higgs particles. And it's stranger than that. If you calculate how much energy the theory says is tied up in all those bonds in that condensate, there's more energy in 1 cubic metre of empty space than the sun outputs in 1,000 years. Per cubic metre. And that's the cubic metre you're in now. So if you imagine a cubic metre cube surrounding you, there are Higgs particles in it, and there's more energy there than the sun outputs in 1,000 years, bound up in the Higgs field. And your particles, the particles that make up you, at a fundamental level, are getting their mass by interacting with that condensate. So the more strongly a particle interacts with the condensate, the more mass it gets. Bizarre idea, but it preserves the beauty of the mathematics. So it was written down, and it was incorporated into the so-called standard model. The prediction, though, is that you must find those particles. If you can get to high enough temperatures, you should realise, make those particles real, as it were, produce Higgs particles. And that was the aim of the Large Hadron Collider, LHC, which is the biggest scientific experiment ever built. So the idea is that the LHC is 27 kilometres in circumference. It lies about 100 metres below the ground in 2 countries. The top half here is Switzerland, that's Geneva Airport runway. This is Lake Geneva, just to get some sense of scale. The bottom bit is France, which is, so most of the machine is in France actually. And the protons rotate around the ring at 99.999999% the speed of light, at which speed they circumnavigate the ring 11,000 times a second. That's called an ultra-relativistic regime, by the way. Einstein tells us that when things move close to the speed of light, strange things happen. Rulers shrink and clocks run slow. And in fact, those protons are travelling so close to the speed of light that time passes 7,000 times more slowly for the protons than it does for the experimenters watching them go around on the surface. Or equivalently, the LHC's diameter is 4 metres from the perspective of a proton. It's an absolutely bizarre regime. So they whiz round, we put them in beams, so not just one proton, but many, many millions of protons in beams, one going one way, one going the other way. We cross them at 4 places on the ring. When we cross them, the beams are compressed into something the diameter of a human hair, but they carry the energy of an aircraft carrier travelling 30 miles an hour. We cross them, and when we cross them, we get on average around 600 million proton-proton collisions per second. In each of those collisions, we reproduce the conditions that were present less than a billionth of a second after the universe began. And the reason we did that was because that should be sufficient to produce Higgs particles if Peter Higgs, with all his aesthetic mathematical machinery, was right. This is just a picture of the inside of the LHC, by the way. Tremendous engineering achievement. These are the beam pipes, the pipes that carry the beams around. I remember one of the engineers telling me, actually, that you think how difficult is this? It's difficult. You've got an electric current going around this 27 kilometres, a load of protons instead of electrons, but it's still an electric current circumnavigating around, but floating in space without a wire. So it's like having a carrying a current all the way around 27 kilometres inside one of those things without any wire. You've got to get it just finely balanced in order to do it. Also, the whole thing runs at 1.9 degrees of absolute zero. Now remember, the cosmic microwave background, the universe itself has cooled down to 2.7 degrees of absolute zero, 13.798 billion years. So this is colder than the universe. It's the coldest place. Without an intelligent civilization,